Okay, now we're going to learn about valence bond theory. This is a more advanced theory about bonding. The Lewis model is great because it's simple, but it's an oversimplification, and there's some things it just can't handle. So valence bond theory is going to employ quantum mechanics. We're going to talk about another one as well called molecular orbital theory. These modern approaches are quantitative. They deal with math, and they predict a lot of the properties that we observe in molecules: bond length, bond strength, geometry, dipole moments, etc. We are not going to look at these theories in a quantitative manner. The math is way beyond the scope of this class. So we're going to look at them in a qualitative way, okay? Just the quality of them. So it's like, you know, the light version of valence bond theory. So let's remember from the quantum mechanics that electrons reside in orbitals. And on an atom, we talked about there are S, P, D, and F orbitals. Remember those funky shapes on the slides, the spheres and the dumbbell balloons and the crazy things, right? Those are the orbitals on an atom. What valence bond theory says is when you've got a molecule, maybe we don't have just those standard atomic orbitals. Maybe they can hybridize and kind of mix together and make some kind of different orbitals. So we call those hybridized orbitals. The idea of a bond here is that orbital overlap is what causes the chemical bond between two atoms. So we have two atoms approaching each other. We've got electrons and a nucleus on one, and electrons around a nucleus on the other. And as they approach each other, the electrons of one are attracted to the nucleus of the other. And valence bond theory is going to look at the changes in energy as these two approach. If the atoms being close together with their orbitals overlapping lowers the energy, a bond forms. If it doesn't lower the energy, a bond will not form. So here we have a graph showing the interaction of two hydrogen atoms. We've got energy increasing on the x-axis, and we've got the distance between the hydrogen atoms increasing to the right. So over here we have two hydrogen atoms that are separated by a distance. In the middle we have zero energy. So if we separated these farther over here, they're far enough away from each other that they're not interacting at all, that the energy is zero. As we bring them closer together, they start to be a little attracted to each other, and the energy goes down a little bit. As we bring them closer together, they interact more, and the energy drops some more. And it keeps dropping, and we get to this point, and the orbitals are overlapping, the energy is lowered, this is more stable. If we keep going and get them closer together, this is kind of like with people, right? You see somebody and you're like, oh, I'm kind of interested in them. And you get physically closer together and you find out you like each other and you're talking and talking. But then there are those people, the close talkers, right, who don't understand personal space. And they get too close to you, right? And that's not cool. And you're like, I'm not so sure about this anymore. There's this ideal distance talking with people, right? You don't want to be too close, but if you're too far away, it's difficult. So that's what's going on with the atoms here. There's a kind of a sweet spot here where the attraction is maximized, the energy is minimized. Just like a ball on a hill, if this was a hill and you had a ball, where would it go? To the bottom, right? Everything rolls down because it's lower in potential energy. And so these atoms are going to be at a distance where the energy is lower, the lowest it can be. And so this is the bond length for a hydrogen molecule. It's the distance between the two nuclei. The energy here, which is negative, is the bond energy. When the bond forms, energy is released. If you want to break the bond, you have to put that amount of energy in. Questions? So the interaction energy is stabilizing, negative, when those atomic orbitals are going to contain a total of 2 electrons that can spin pair. So orienting in opposite spins, one positive, one negative. Usually this is going to happen when you've got a half-filled orbital on one atom and a half-filled orbital on the other atom. They overlap. The electrons pair, just like they pair in the atomic orbitals. Remember, you have to have one arrow pointing up and one arrow pointing down. And that'll give you a bond. That's usually what happens. But you can also have what's called a coordinate covalent bond, where you've got a very generous atom, let's say, with a full orbital, and then a very poor, needy atom with an empty orbital. And their orbitals can overlap and form a bond even though both electrons came from one atom and not from the other. That can happen as well. It's just not as common. It's called a coordinate covalent bond. So the two atoms with their half-filled orbitals approach each other. As the orbitals overlap, the electrons are going to align with opposite spins. So, summary, valence electrons of the atoms in a molecule reside in quantum mechanical orbitals. The chemical bond is the overlap of half-filled orbitals. They spin pair. The geometry of those overlapping orbitals is what determines the shape of the molecule. Okay, so this isn't just based on thinking about electron groups. It's actually looking at the orbitals and their shape. So let's look at dihydrogen sulfide. So here we have orbital diagrams. Here's for hydrogen. Hydrogen only has one electron. It's in the 1s orbital. So it's got a very simple orbital diagram. In all of this, we're just looking at valence electrons. We're not looking at core electrons. So here's an orbital diagram for sulfur. Its valence electrons are in the third level. And so we've got 3s2, 3p4. We want to look at the orbital diagram, though, because we want to see which orbitals are half-filled. So valence bond theory says, well, this is going to form bonds by this orbital overlapping with that one. And so over here on this picture, for sulfur, the blue here is the s orbital, and it's got a pair of electrons in it. And each of these pairs of red balloons, that's what they look like, is one p orbital. So this one is filled, that's this lone pair right here, and the other two are half filled, this guy and this one. And they can overlap with a half filled s orbital on the hydrogen. And when they overlap, the electrons pair up and that forms a bond. It makes sense? If this isn't, if you've got questions, ask them now, because we're going to expand on this, okay? So the actual bond angle from observation is 92 degrees. Valence bond theory predicts that this bond angle would be 90 degrees because that's how the p orbitals are arranged. VSEPR theory just says, well, it's going to be less than 109.5. So things are agreeing okay. Some of these are estimates and they're not going to be perfect, but so far so good, right? Let's look at another one. Okay, and this is a new section, so I got to stop.